So let's start with this point as PCA, named as Principal Component Analysis. This is one of the techniques of feature extraction. This is the most popular one. For principal component analysis, if I want to say, it is a unsupervised learning algorithm that is used for dimensionality reduction in machine learning models. More probably, you can say it is a statistical process that converts the number of observations of your correlated features into a set of linearly uncorrelated features with the help of orthogonal transformation, right? Now, these new transformed features are called as principal components, right? There will be different orthogonal perspectives, different orthogonal transformations, and based on these transformations, we will be deciding it as one of the principal component. So if I have multiple PCs, principal components, so I'll state first as PC1, the other as PC2, then other as PC3, and then I will decide which principal component to choose and which to extract, right? Meaning, so this is one of the techniques for feature extraction. Now here, principal components we define as one of the newly transformed component, right? And we name it as principal component. So if there are multiple components, what we do is we try to make an analysis of all those all together and then try to analyze what will be the further input provided to your model. This is one of the most popular tools in machine learning, which is basically used for your EDA, basically named as exploratory data analysis, and for predictive modeling. It is a very good technique to draw your strong patterns, or you can say strong similar patterns matching to your data set to give the perfect answer from the given data set by reducing the variances, right? How variance one PCA will be differing from another. So how much is the variance between two different principal components? By deciding or by comparing this, what we do, we try to deviate that, right? So PCA, that is principal component analysis, generally tries to find the most lower dimension surface to project the highest dimensional data, right? So PCA works by considering the variance of your each attribute and then try to split it in a very good manner between, you can say, the classes by reducing the dimensions, right? As we saw some applications for image processing, most probably for movie recommendation system, right? Or any kind of, you can say, machine learning model. So it is a kind of feature extraction techniques, right? What happens here is it will try to find out the more important variables and then try to drop the least important variables. Now, even though I drop these least, there will be some amount of record or indexed holding that these are least important and these are the most important variables, right? We do not totally delete it or unlearn it. We are learning that these are least important and these are the most important, right? Now, what we will be focusing by using PCA only on the most important variables, right? And we will be not focusing on the least important variables, because that data, because of these least important variables, I might affect my accuracy, right? So if I lose this, I'll try to evaluate how much. If I'm having 10 different variables and 5 are most important and 5 are least important, so I'll try to first iteration, I'll try to analyze that. What if I lose 2 least important variables and perform with 5 most important and 3 least important? What is the accuracy? On the second iteration, on second component analysis, I'll try to reduce one more, 5 important variables and 2 least important variables. Then accordingly, I'll try to test my model that how good it is going towards the best fit line. Based on these reducing of dimensions, PCA will give you this kind of analysis. Let's see a small example. There are two different concepts related to this kind of PCA. First, we have is the variance and covariance. And second is the eigenvalues and eigenfactors. See, first, when I have least features, right? I do not have lots of data. I only have on one dimension as d equal to 1. So I have all the points stated on only one axis on a number line as a number system, right? So I do not have much amount of data to explain over here. So what I do is I increase my dimension as d equal to 2. Now I have two variables, x1 and x2, which defines and stores lots of data compared to d equal to 1, right? Even though if I feel that this is not sufficient, what I do, I increase one dimension and find out the other perspective, how more efficiently I can store data, right? Now this was how your data sets went on growing large. But apart from these, d1, d equal to 1, d equal to 2, and d equal to 3, all showing that data can be stored in a very large form. But is this large storage data really essential for me to help get my model more accurate, right? So this is how we represent our data. One dimension on a number line system, two dimension in a grid of structure, or you can say in an array form. So this will be representing as x2 comma x1, and similarly all these grids will be representing on x and y axis. This is your third dimension. You can see each block will hold 6 different values indicating the third dimension. Right, so this is the small example of how principal component actually is. If you have one dimensions, two dimensions, three dimensions, and lots of different other perspectives. Now there are different terminologies looking towards this. Suppose you're having these kind of functions as f1 to f7. Now in this kind of structure, what we do is we are trying to find out what our actual data set consist of different features, right? So my features are f1, f2 to f7. Now after applying principal component analysis, what I will figure out is trying to find out the most important and the least important features amongst these original features, right? So after applying principal component, what I find out is, you can see here, right? It will be from components importance will be in a decreasing order from most important to least important. Now here I can find out that if I'm having 7 total features, right, from f1 to f7, and after applying principal component analysis, I'm having the exact original features. None of them are reduced or unlearned, right? None of them are deleted from my data set. They are present in the data set, indicating they are either least important or either most important, right? So now this part, PC1, will be your most important feature into your entire data set, right? I cannot lose PC1, because if I lose PC1, maximum amount of accuracy will be lost. That means there's a relationship between these features, amongst these features, from f1 will be dependent on f2, f3, f4, f5, f6, and f7, right? Each feature will be dependent on each other feature, but how closely or how tightly it is being coupled with each other. If I want to relate, I want to focus more on f1, and I want to reduce my dimensions, not losing my actual meaning of data set. Which of the features can I lose? So after applying principal components, I can see that if I want to more focus on PC1, I can leave PC7. Meaning will not change, meaning will remain the same, because this is considered as the least important into my entire data set. What PCA does, it tries to reduce your dimension. Now it is up to the user or up to the developer who is going to develop the machine learning model, how much features to be reduced so that its meaning of your actual data set remains the same, but your actual features are reduced from 7 to some number, but not 7. Right? This is the idea behind running PCA. Right? So this is considered to be one of the most popular techniques in feature extraction. Now what we have done is we have extracted all these features aligned in a descending order. Then PC1 will be the most important, PC7 will be the least important. Now I will have different iterations, excluding PC7, then testing the accuracy, excluding PC6, then testing the accuracy, and so on. I'll be checking that if I lose 4 features among all these 7 from PC4 to PC7, I might lose my accuracy because my data set's meaning is now about to change, right? So if I again add PC5 as one of the feature in remaining 4, then I see that the accuracy was reduced, now it is increased. If I add PC6, right, that is considered as the second last least important feature. Even though I add it in PC5, nothing change is there, nothing, a lot more amount of growth in accuracy is not there. At that moment, I can decide that PC6 and above all features are not that essential to be considered in my model set. Right? Now here, 2 features are reduced. That means the processing time taken to compare it with other remaining features will be reduced. That means overfitting condition will also be reduced. There's no risk of going overfitting for your model. So you can decide that PC1 to PC5, if I'm having these features, will give me the maximum output and the best accuracy. So this is the actual concept of principal component. Now these are the different, you can say, terminologies which are being used in PCA. First is the dimensionality, that is what kind of, you can say, what do we reduce it, right? So dimensionality is nothing but the number of features which are present in the given data set. Second is the correlation. As I said, we're having 5 different PC1 to PC5. How each feature is, you can say, dependent or more describably loosely or tightly coupled with any other feature. That is nothing but the correlation. Then we have orthogonal, that defines the variables are not correlated to each other. And then when the correlation is 0 between 2 different variables or pair of variables, we call that as orthogonal, right? Eigenvectors and eigenvalues we have, there's a square matrix of n with the non-vectors variables as v. So this v of non-vectors will be decided as an eigenvector. And lastly, we have covariance. So correlation and covariance are, you can say, work hand in hand. Covariance is nothing but a matrix which represents the covariance values, pair of values between the 2 variables, right? So we have a grid of number of variables indicating from 1 to 1 from the last variable, comparing with each kind of variable, right? So if I'm having here as PC1 to PC7, here. So I'll be deciding that PC1 is how much strongly or loosely coupled with PC2, similarly with PC3, with PC4, PC5, 6, and 7, right? So there will be a grid of all these relationships. Similarly, PC2 to PC1, PC2 to PC3, and so on. So what I do is I have a grid of all these, and it is represented as a matrix. Now, these are the steps how you can implement PCA. Obviously, this cannot be again being solved onto your by using pen and paper, because there are lots of you can say possibilities or different perspectives to be analyzed. Just as I have seen a simple example of 7 features. For 7 features, you can see we can have n number of possibilities. So that all have to be evaluated, because what are the most irrelevant or the most unimportant, we need to identify that. So what is the first step? First step is to get the data, your actual data set, represent the data set into a structure, right? What we do is we remove all those null values and all, right? You get a clean data here. Standardize the data. Standardizing data means we use normally standard scalar. That means all the values will be representing between -1 to 1. Hmm? Then we calculate the covariance, how these features are strongly or loosely coupled to each other. Then based on these values, we make their vectors for eigenvalues and eigenvectors. Then we try to sort those eigenvectors. Now, after sorting this, we put up it into a descending form, that is from most relevant to least relevant. This is where we try to calculate the new features for our principal components. Now, after identifying and putting it in a sequence from most important to least important, now what we need to do is we need to identify the most only and remove the or do not take the cognizance of unimportant features into your new data set, right? So after implying principal component analysis, least important or the unimportant features will be skipped away, not removed entirely from your data set, but will not be taken into consideration. Only the most important features from your new data set after applying PCA will be taken into consideration, and that data set will be provided to your model. Okay, so you can take a snapshot of this. These are the different steps for implementing PCA algorithm. PCA stands for principal component analysis. Principal component means one of the feature. After implying all these 6 steps, you get multiple principal components as PC1, PC2 up to PCN. So those are nothing but your principal components. After making an analysis, you put all those PCs into a descending from most relevant to least relevant data. So you remove the unimportant features or the most irrelevant data and try to keep only the important features. Remember, without changing the meaning of your data set, right? What you are going to achieve, the identity must not be lost for your data set. Okay.